Alice and Bob have been kicked off a plane. Alice has a parachute, Bob does not. What are their chances of survival? Let's find out. Well, to start with, it depends a lot on whether they're on Earth or not. You see, the speed they fall at or the speed they reach ultimately when they fall depends on gravity and on the atmosphere. This speed is what's called terminal velocity, and this is pretty important because what kills you is not the fall, it's the impact. You could keep falling forever with no ill effects, basically, other than maybe boredom and eventually, the lack of supplies. But falling isn't going to do anything to you. The real problem is the impact because it causes enormous forces on your body, which is what causes all the damage actually. Don't ask me about the exact damage though. My area of expertise is not medicine, but I can explain the physics of the situation. Again, what we were talking about was the impact. Terminal velocity is important in this case because the force on you during the impact depends a lot on your speed. So you can see the equation on screen right now. That is Newton's second law in equation form. Force is proportional to rate of change of momentum. And if your mass is constant, as it tends to be unless you're a rocket or something, the force on you would be simply given by F equals ma, as in the force is equal to mass multiplied by the acceleration. Now, for the purposes of this discussion, let's assume that the acceleration is linear. That is, when you crash into something, your acceleration from your falling speed to your final speed, that is zero, is linear. It's not, but the conclusion we arrive at from that assumption is valid. So if you assume the acceleration is linear, you could write the force like this using this equation, where VO is your final speed, which is zero, as I just said. Vi is your initial speed, that is the speed at which you impact, and t is the duration of the impact. That is the time taken for you to slow down from your landing speed to zero. What this means is the higher the initial speed, the higher the force. Also, if the impact time is shorter, the force will be higher as well. So if we look at cushions or parachutes, that is what they do basically. A parachute reduces your landing speed, and a cushion, if there happens to be a cushion in your way, what it does is it increases the time needed for you to slow down. So that is how it reduces the force on you. That's enough about the impact force. So let's move on to terminal velocity because, as we saw, the higher the speed you fall at, the greater the force on you. And terminal velocity is the speed you ultimately reach when you're falling, provided you fall from high enough. Okay, so to discuss terminal velocity, let's assume Alice and Bob are marbles. Let's just list the forces on them and start the calculation. For Bob, we have his weight acting down on him. This depends on his mass and the gravitational acceleration acting on him. If he's reasonably close to Earth's surface, then 9.8 is a fairly good estimate. It could be lower, like if he was on Mars, or higher if he was close to, say, a heavier planet like Jupiter. So Jupiter doesn't actually have a surface, but yeah. So it's safe to assume this will be constant under most circumstances. That is the gravitational acceleration and therefore the weight. The other forces acting on him is air resistance. This is a fairly complex force. One part of it is skin friction, that is the friction between the surface of the marble and the air. And another part of it is caused by aerodynamic forces, that is, the interaction of the falling body, in this case the marble, with the airflow around it. Another factor that goes into this component is the density of the air around it. So the thing with this force is it's not as simple to calculate, but it can be modeled reasonably accurately as being proportional to the square of the speed at any given time. So that is basically we are going to model it as kv squared, where k is a constant. So both weight and air resistance are forces. So we can plug this to find the net force and plug it into Newton's second law and use that to calculate the resultant force on the marble, as we see here. So this is a fairly complex equation to solve because we have acceleration and velocity, and acceleration is the derivative of velocity. So we are going to need calculus to solve this equation. But instead, we are going to plug in some values, basically plug in some random values, and I'll show you what Bob's speed looks like, provided he was falling for the whole time in atmosphere. So as you can see on the graph, his speed increases rapidly at first, but the rate of increase starts to slow down and it finally reaches a constant speed. And this is because as the speed increases, by our equation, air resistance increases as well with the square of the speed. So this happens until at one point it balances the weight of the marble entirely, and at this point the resultant force on Bob is zero. So if you're looking at Newton's first law, he will continue to travel at the velocity he was at until another force acts on him to stop him. That is basically until he lands. So again, the speed that he reaches ultimately, in this case it's about 1.4 on the scale, is the terminal velocity. So the values are taken here are completely arbitrary. The actual terminal velocity of a human is 200 290 kilometers per hour on Earth, obviously. The terminal velocity of a normal marble is about 80 kilometers per hour. The terminal velocity of a human-sized marble, well, the less is said about that, the better. Because given its high mass and highly aerodynamic shape, it's probably well in the realm of ludicrous speed. So now let's take the case of Alice. Remember, she has a parachute, and the parachute has a large surface area facing the flow of air, which produces a fairly large air resistance. In terms of the rough equation we looked at, it's equivalent to increasing the value of the constant k. So in the graph below, I've increased the constant k by a factor of 3. And I've also zoomed in the first zero point 0.5 time units because that's where we can see the difference clearly. So there are two things to note here. One, Alice stops accelerating at a lower speed than Bob. That is, she has a lower terminal velocity. And two, Alice reaches that speed slower than Bob. Sure, Bob takes longer time to reach his terminal velocity, but if you're looking at Alice's terminal velocity, Bob reaches that speed much earlier. If the parachute produced more air resistance, Alice's top speed or Alice's terminal velocity would have been even lower. And actually, there is a neat equation you can use to calculate terminal velocity of something. The equation is here. So you have to know the mass, gravitational acceleration, that is g, rho is air density, a is the projected area of whatever's falling. Basically, think of the hole in the floor if whatever it was fell through the floor like a cartoon character. And CD here is the coefficient of drag. This can be assumed constant for a given case. So it's going to change with an object's orientation to the wind and a lot of other factors, but we can assume it's constant for this case. I gave you the early equation so that you can see the mechanisms at work and see how we reach the terminal velocity when something's falling from a considerable height. And another thing to note is if you compare the equation for terminal velocity with the very rough equation we looked at, you would have noticed that K in our equation kind of includes air density as well. And therefore, the denser the atmosphere, the higher the air resistance. And consequently, the lower the terminal velocity. You can see that if you look at this equation as well. And another important thing to note is if the pressure was high enough, your terminal velocity could start to approach zero. I mean, if you're in a fluid that was that dense, either the pressure could crush you or you'd be in water. But let's ignore that for now. Let's just focus on the falling part. So that is probably useful information if you're setting your story on a planet with a dense atmosphere. Another variable you can consider if you're planet hopping is gravitational acceleration. This increases with the density of the planet itself. The higher the gravitational acceleration, the higher the terminal velocity, and vice versa. All this was based on the assumption that you have an atmosphere. What if there's no atmosphere? Like, say, you're on the moon. Well, in that case, there is no air resistance, so no terminal velocity. And because there's no air, there's no point in having a parachute either. It's practically useless. So, what this means is there's basically nothing to slow your fall. So, here the damage is actually going to depend on how high you were when you started falling. You might stay in the moon surface or bounce gently off the surface because you will accelerate for as long as you're falling. So one more thing I wanted to add with planets that have an atmosphere, reaching the terminal velocity might take a reasonably long fall as well. So if you fall from say 10-20 meters on Earth, you're not going to reach terminal velocity. You'll be still accelerating when you hit the ground. But the difference is if the planet has no atmosphere, you're never going to stop accelerating, even if you jump off a plane. So that's it for a brief overview of some important things to consider about a fall and the effects of impact and terminal velocity. So this was a very broad overview. If you have any questions, you can ask in the comments and I'd be happy to answer them. See you next time.